So what was the inspirational good deed that you'd like to submit?
I want to thank Cheng for helping me with 2 web assigned questions that I couldn't figure out.
Awesome.
He showed me some pictures on napkins and it made a huge difference.
Cool. Great. Now, how do you say your name?
Cheng.
Cheng Jiang?
Cheng.
Cheng Jiang.
Cheng.
Cheng Jiang?
Cheng.
Cheng
Cheng is the man, he's going live. He gets 54 out of 65. He knows what he wants and he wants to thrive. Cheng, he belongs to the science tribe. Cheng is the man, he is so kind. A better friend you will never find. He helps you improve your state of mind. It's truth that he seeks and it's truth he finds. Yeah. Cheng is the man, he's going live. He's got the brains and he's got the drive. Taking physics and math from 9 to 5. He's so in the flow, he doesn't need to strive. Cheng is the man, he takes no jive. On all his APs, he's gonna get a 5. He gets out of school at 1:45. Give it up, this man deserves a high five. Yeah. Yeah. Cheng is the man, he has arrived. He jams on the sax when he plays it live. He's got the brains and he's got the drive. But I can't say his name right to save my life. No, I can't say his name right to save my life.
Whoa, that just happened. Pretty amazing. But what's more amazing is that with only these 3 equations that you're looking at right there, you can do all the problems from this chapter. In fact, you may only need 1 of the equations. Please keep those inspirational good deeds coming so I can do more raps. I can't promise anything with that production value, but I really want to do some freestyle, so keep submitting those good deeds. Let's go ahead and start with what we're talking about this week, which is static equilibrium. Now, static equilibrium is actually great because it's one of the easiest chapters we have. There is actually no new physics. In fact, all you got to use is these 3 equations with all the old physics, and you will have it mastered. But it really is important to use the fact that this is an easy chapter to go back and review to make sure you understand everything about torques and rotation, angular momentum, all that stuff. So this is a great time to review. I did want to thank a bunch of people for help on the video, including the AP Physics classes, Antra Lakaya and Mara, John, and especially Cheng. And I'm with apologies that I still can't say your name right, but I'm getting there. Let's go ahead and get into some static EQ. First, what is static equilibrium? Well, in order to know that, you really got to know what static means. Static simply means that V is equal to 0. The speed's equal to 0, but also the angular speed or velocity is equal to 0. The object is not moving. Now, this combines with the concept of equilibrium, where the net force is equal to 0. That means the object's in translational equilibrium. And the net torque about an axis is 0. It means it's in rotational equilibrium. So you put them all together, static equilibrium is where you have V equal to 0, omega equal to 0, the angular speed, the net force equal to 0, and the net torque equal to 0. So notice all those must be true for an object to be in static equilibrium. It's not enough for it just to be at rest. Notice I throw this up for an instant up here. It is at rest, but it's not in equilibrium. There's a net force on it. One thing that's real important here is that if the net force is 0, you can establish that, and you can find an axis where the net torque is 0, in other words, you can find any axis where that's true, that means that the net torque is 0 about every axis. So in other words, if you can establish there's one axis about which the net torque is 0, and the net force on the object is 0, then you can actually analyze about any axis you wish, which is very convenient for us. Now, to see if you get this, let me ask you this question. If I have a net force of 0 on an object, my question to you is, must the net torque be 0 on the object? Think about that for a second. Can you have a situation in which the net force is 0, but the net torque isn't 0? Well, in fact, you can. Take a look at this situation right here. We've got an object, a spinning disk with an axis of rotation right there in the center. The force on this, the net force, is 0. But notice it's still going to accelerate angularly around that way. So the net torque is not 0. Cool. Let's take a look at some problem-solving hints for this chapter. These are incredibly valuable. Okay, so let's start with this. You draw a free body diagram of the object. Now, you guys know how important I think these are. This is especially important for this chapter as well as the last couple chapters. And also critical is that you put the arrow tails at the point of force application. This is essential for this chapter as it was for last chapter and the chapter before. We have to know where the force is acting in order to figure out torque. So you must put the tails of the arrow directly at the point of force application. Now, when you draw your free body diagrams, which are especially important as usual, you're going to try to guess the correct direction of the force. Now, if you can't, it's all good. If you pick the incorrect direction, you might find a force when you solve for it is less than 0. That just means it went in the opposite direction. That's not a problem at all. It'll just come out negative if you've guessed the wrong direction. You also want to use the lever arm wherever possible. Very, very useful for this chapter. Use the lever arm, i.e. the moment arm, whenever possible to determine the torques about the axis you have selected. In fact, we want to choose a convenient axis for our torques. What makes an axis convenient? Well, if there are many forces that you don't care about that act at a specific point, you might think about making that the axis of rotation that you're analyzing about, because those forces that are acting right there at that axis will exert no torque. So if you don't want to deal with some forces, you just pick the axis where they're acting and they will not contribute to torques. Now, that's not always the best idea, but with practice we'll get better. You also have to choose a positive direction for tau, the torques, and it should correspond to the positive direction for forces. In other words, if you make clockwise positive for rotation, anything that moves down when the thing's moving clockwise, that has to be the positive direction for translational motion as well. So your rotational motion and your translational motion have to agree in sign, S-I-G-N. Again, if you can find a situation where the line of action of a force goes through the rotational axis, then that lever arm, in other words, the displacement from the axis of rotation to the line of action of the force is 0, and therefore the torque about that axis will be 0 due to that force. Here's an example right here I just want to take a quick look at. This person is standing on top of a Ferris wheel, right on the top in the center. And that Ferris wheel has an axis of rotation right there in the center. You'll notice that the force on them, mg, you draw the line of action, it goes through that force all the way through, forward and backwards, and you'll see that it goes right through the axis of rotation. In other words, the lever arm, the displacement from that axis of rotation to the line of action of the force, that line, is 0. So the torque caused by that force about that axis is 0. When the line of action goes right through that axis of rotation, d, the lever arm, is 0, thus the torque will be 0. By the way, you can calculate torque just by d times f, because torque is r cross f, and that means rf sine theta. D, reminder, is just r sine theta. Cool. So then the final step, and what is so easy and awesome about these problems is this. All you got to do is write these equations, and it's always the same equations for every static equilibrium problem. Every one of them. In fact, it may only be one of these equations, but if you see a static equilibrium problem, you know all you got to do is write down the net torque is equal to 0. You got to write down the net force in the x direction is equal to 0, and the net force in the y direction equals 0. those will always be the three equations. Now, in fact, you may actually only need one equation. I recommend to always start with this torque equals 0 equation, because for many examples, that is the only equation you will need. So this is an awesome time to review all your old physics, torques, rotation, angular momentum, so that you can use them here. But all you need is all that old physics and know that these are the three equations that will apply every single time for every single problem. Again, it may only be one of them. All right, so this whole lecture just consists of me showing you a bunch of example problems, because now we have already covered all the physics. All right, I'll see you in the next video.